Hi, welcome to Brilliant Qatar PYQ discussion video series, and in this video we are going to discuss previous year's questions from the chapter Nuclei. Let us do some MCQ questions first. See, as we know, the chapter is a very small chapter. We have only few concepts in the chapter altogether. So let us go through the questions and we'll. The mass density of a nucleus of mass number A. The first question is about the nucleus, density of a nucleus. And we have learned density of a nucleus. What is the relation between density of the nucleus and mass number of the nucleus? See, and we know it is independent of the mass number. Right? Nuclear density of nucleus is independent of mass number. See, we know how to calculate density of nucleus. Density of anything is going to be mass by volume. So mass of the nucleus divided by its volume. And we know how to calculate density, mass of a given nucleus. Mass of a given nucleus is going to be total number of nucleons, which is also called mass number, into mass of one nucleon, which is one atomic mass unit, divided by, see, that gives you the total mass of the nucleus. Total number of nucleons times mass of one nucleon gives you mass of one particular, one nucleus, and then be divided by the volume. Volume of the nucleus is considered to be 4/3 pi r cube. Right? Yes. And in this, A into U in the numerator is as it is 4/3 pi into, what is R? R is the radius of the nucleus, and we have the relation radius of the nucleus R is equal to R0 A raised to 1/3. Right, where R0 is the constant, 1.2 FM, we know that, and R0 into A raised to 1/3 the whole cube, because we had 4/3 pi R cube as the volume. See, in this one, we can write this as AU divided by 4/3 pi R0 cube into A, right? A raised to 1/3 the whole cube is going to be just A only. We can cancel A from, that means the density, nuclear density, is actually independent of the mass number. So option D is the correct answer. Right. Question number 2. Two nuclei have their mass numbers in the ratio 8:1. Right. The ratio of their nuclear densities. See, this question is actually really confusing. We may be asked to find out what is the radius ratio, right? Radius of the nuclei 1 to the radius of the nucleus 2, R1 by R2, or you may be asked to calculate the density ratio, density of the nucleus 1 by density of the nucleus 2, right? Of 1 to 2. See, if it is radius ratio, we know the relation R is equal to R0 A raised to 1/3. It depends on the mass number, and you are given perfect cubes, right? So if you go for R1 by R2, we get A raised to 1/3 and A1 raised to 1/3. R1 by R2 is going to be mass number 1 by mass number 2, the whole raised to 1/3. But that is only for radius of the nucleus. The question is about what is the nuclear density ratio. Just now in the previous question, we explained that nuclear density is independent of mass number, right? Independent of A. So whatever be the mass number, that doesn't affect, the ratio is going to be 1:1. But be careful, if the question is about radius of the nucleus, answer will be different, right? We know. Okay. Now, the difference in mass of X7 nucleus and total mass of its constituent nucleons is 21U. That U is the atomic mass unit, we know, right? 21U. The binding energy per nucleon of this nucleus is equal to the energy equivalent of. See, the question is based on binding energy per nucleon calculation, right? Binding energy per nucleon. We know binding energy of any nucleus is calculated as the delta M. What is the delta M stands for? Missing mass, right? Delta M into 931 MeV, right? This is the energy equivalent of one atomic mass unit. Energy equivalent of one atomic mass unit is 931, right? Energy equivalent of one atomic mass unit. So we multiply that value with the mass defect, delta M. So then we will get binding energy. And how will you calculate binding energy per nucleon? Binding energy per nucleon of the nucleus is going to be total binding energy divided by its mass number. Okay, total binding energy by its mass number. Good. Now, the given question, the question says we have a nucleus. That nucleus has a difference between the total mass of its constituent and the actual mass. See the difference between mass of the nucleus, actual mass of the nucleus, and mass of the constituent particles. So they are talking about the delta M, right? What is that delta M stands for? Delta M stands for the difference between actual mass of the nucleus minus its mass of the constituent particle, right? Mass of constituent particles. This value is already given in the question. What is it? That is 21 atomic mass unit, correct? Delta M is given as 21 atomic mass unit. Okay, that is what the question is all about, right? The total mass of the given mass of the nucleus minus the total mass of its constituent particles, which is nothing but missing mass or the mass defect. That value is given. Then binding energy of this nucleus can be calculated as that 21 into 21 atomic mass unit into 931, as I told you before, right? We multiply with 931. Now, you're asked to find out binding energy per nucleon, right? Look at the question. It is not about binding energy. It is binding energy per nucleon. So what will be binding energy per nucleon? From this calculation, we can say binding energy per nucleon is going to be total binding energy by mass number, right? What is the mass number of this nucleus? Mass number of the nucleus is given as 7. Look at that. See? X7. So we have binding energy is 21 atomic mass unit into 931 divided by 7. And we get 3 atomic mass unit into 931 MeV. This is the binding energy per nucleon. Now look at the options. In the options you have given 3U, 3.5U, 7U and 21U. Look at the last part of the question. See, binding energy per nucleon for this nucleus is equal to energy equivalent of. See, we got 3U into energy equivalent of 1 atomic mass unit. So what is your matching option? See, 3U, right? Energy equivalent of what? 3U. That is the binding energy per nucleon of that particular nucleus. So the concepts related is what is binding energy, right? How to calculate binding energy. Binding energy is the difference between the actual mass of the nucleus and the total mass of the constituent particles. That was given directly. Delta M was given directly. So we found total binding energy divided by mass number gives you the binding energy per nucleon. Fine. Okay. Question number 4. Which of the following statements is not true for nuclear forces? See, we know nuclear force, right? It is a force acting between the nucleons inside the nucleus of an atom, right? And that force is only seen within the nucleus only. And that force have some properties. We know, look at the statements given. We have to identify the one which is not true, right? The wrong statement you have to pick. See, they are stronger than Coulomb forces. First statement. That's a true statement because nuclear force, right? Nuclear force is the strongest force in nature. Strong nuclear force. Strongest force in nature. Right. Then they have about the same magnitude of different pairs of nucleons. That also we know. We learned one of the property. These are charge independent. Nuclear forces are charge independent in the sense, if you consider proton and proton pair, see inside the nucleus we have both protons and neutrons. So the nuclear force may be operating between protons and protons, or it could be between protons and neutrons, correct? Or even it could be between neutrons and neutrons. They remains the same. Magnitude of the force remains the same for all these pairs. It is charge independent. Yes. So they have about the same magnitude for different pairs of nucleons. Is a true statement. Good. Now they are always attractive. That is the third point given, right? And that's supposed to be the wrong option, wrong statement, because you know nuclear force is not always attractive, right? It could be even repulsive also in some special cases. We know the condition. We will discuss that in one of the questions later. We have that graph to explain, potential energy versus internucleon distance graph. And we know when the distance between the two nucleons becomes less than 0.8 FM, the force becomes repulsive. So we can't say it is always attractive. It can be repulsive also in certain conditions. So that is a wrong statement. They saturate as the separation between the two nucleons increases. Saturation property of nucleons, right? That also we know, nuclear force. So that's a true statement. So option C is the correct answer. Okay, question number 5. The ratio of nuclear densities of two nuclei of mass numbers 64 and 125. We know this. See, we have this particular concept discussed in one of the previous questions. We are going to calculate nuclear density ratio, which is independent of mass number. So we have option D, right? Whatever be the mass number of the nuclei, that doesn't matter. Ratio of their nuclear densities remains the same, 1:1, independent of mass number. Okay. Now, the radius of the nucleus is, see this part, you are asked to find the relation between the mass number, see mass number, atomic weight, then again mass number, and none of this. So what is the relation for radius of a nucleus? How to obtain expression for radius of a nucleus? We know the equation. We calculated size of the nucleus, right? Size of the nucleus is found to be proportional to like the mass number. Which means if you go for higher elements, it has to accommodate more nucleons, right? So the size of the nucleus should be more. To accommodate more nucleons, definitely should be of bigger sizes. And that size is represented in the terms of volume, So we would say volume is proportional to the mass number A, right? Size increases means we consider nucleus as a spherical shaped like central core of an atom. So its volume is considered to be 4/3 pi r cube. If it is a spherical shaped one, 4/3 pi r cube is proportional to what? Mass number. So we already have a constant in the LHS, 4/3 and pi are constants. So we can say r cube, radius of that particular nucleus, is proportional to the mass number, correct? R cube is proportional to the mass number, or R is proportional to cube root of the mass number. Yes, so that was the equation we got, right? And then radius R, we know is R0 a raised to 1/3. We mentioned this equation before in one of the questions. So R is equal to R0 a raised to 1/3 is the exact relation. R0 is a constant, which is 1.2 into 10 raised to minus 15 meters, right? That is the value of R0, right? So now look at the options given. We can say directly proportional to its mass number, inversely proportional to the atomic weight, directly proportional to the cube root of the mass number. See, R is directly proportional to a raised to 1/3. Right. So that is the correct option, option C. Okay. Next one. Nucleus of an atom whose atomic mass is 24. See, nucleus has an atomic mass or mass number 24. That is what the given information about the nucleus, and you have given 4 options. You have to choose the correct one. Okay, see, this one, we have option A, 11 electrons, 11 protons, and 13 neutrons. See, we will think like if 11 electrons are there, there should be 11 protons also, because electrons and protons number should be equal, but that is in an atom. Right? In an atom. Yes, in an atom it is true. If there are 11 electrons and 11 protons, the remaining should be neutrons, right? The 13. So if we check in that sense, many options may be correct. But we are talking about what? We are talking about a nucleus. Nucleus of an atom consists of. So there itself we have a hint. Inside the nucleus, there is no electrons, right? No electrons possible. So electrons options we can strike off. There is no electrons inside the nucleus. We are not talking about the atoms. We are considering only the nucleus of a particular given atom. There is no electrons inside. So now check C and D. 11 protons and 13 neutrons. See, that is the only possible option because there is electron in the last option also. So option C is the right answer. So even if you don't know how many numbers are present, doesn't matter. If you know in the nucleus there is no electrons possible, then you can go for the correct option, right? Option C. Okay. Now, next question. MP denotes the mass of proton and Mn that of a neutron. Okay, mass of proton and mass of neutron represented as MP and Mn. The given nucleus of binding energy B contains Z protons. We know this. Z is the atomic number of a given atom. That many protons will be available there. And N is the number of neutrons. The mass M, N, Z, okay, of the nucleus is given by. So we are asked to find out what is the actual mass of the nucleus. Mass of the nucleus is to be calculated, correct? Mass of the nucleus we have to find out. In terms of what are the given values? B stands for binding energy. Yes, question says B is the binding energy. Mn is mass of neutron. Mp is mass of proton. Z is the number of protons available and N is the number of neutrons available. Yes, so we know binding energy calculation. Binding energy is equal to delta M into C square. Energy equivalent of the missing mass. Energy equivalent of the mass defect. That is binding energy of a nucleus, right? Okay, see if it is binding energy is calculated like this, given that binding energy is B. So let me say B is equal to, what is delta M? Delta M, just now we mentioned in one of the questions before, delta M is the difference between actual mass of the nucleus and its constituent particles, right? Total mass of the constituent particles will always be more than the actual mass of the nucleus. So total number of nucleons is going to be Z number of protons into mass of proton plus how many neutrons? As per the question, it is N. N neutrons into mass of neutron. See, this is the expected mass of the nucleus, right? Total mass of the constituent particles minus actual mass. Yes, minus actual mass. So now this makes the delta M. See, delta M is the missing mass into C square is the binding energy. Correct? So missing mass is the difference between expected mass of the nucleus, or it is the total mass of the constituent particles inside the nucleus minus actual mass of the nucleus. Okay. So now we have to find out what is the value of this M. One of the matching option will be there. That's it. So just open the bracket. So B is equal to, we can say B is equal to Z times MP plus N times Mn into C square minus MC square. Correct? I just opened the bracket. I need M to this side because I have to calculate the actual mass of the nucleus, M, right? Mass of the nucleus, M is to be calculated. M is equal to, see, Z mass of proton plus N mass of neutron, the whole into C square minus B, right? But there was a C square also here. If you take C square and MC square to the LHS, this is what you will get. Now, what happens if you take the C square to the other side? This C square will be cancelled and there will be B by C square, correct? So we can say Z MP plus N Mn, that C square is cancelled, minus B by C square. Because I have to take this C square to the RHS, when I take C square to the RHS, first term C square gets cancelled. In the second term, they will be divided by C square, okay? So Z times MP and N times Mn minus B by C square, and that is option D, right? This is the correct answer. Number of protons into mass of proton plus number of protons into mass of proton minus B by C square. Okay, that is the expression for total mass of the given nucleus in terms of binding energy. Okay, so that is option D. Now, let's move on to the next question. The curve of binding energy per nucleon as a function of atomic mass number has a sharp peak for helium nucleus. This implies that helium nucleus has one of these following properties. We have to choose the correct option, and the question is about that binding energy per nucleon graph. Binding energy of a given nucleus versus mass number graph, right? So we have mass number taken along x-axis, binding energy per nucleon is taken along y-axis. And we know the graph, it's like if this is 8 MeV reference line, so it is varying somewhat like this, right? This is the way how that binding energy per nucleon graph can be represented. And in this, you can see some peaks in the graph, in this part, right? And this peak in the graph actually stands for some of the nuclei in this region are more stable than the neighboring ones. See, the nuclei coming in these peaks, they have extra stability, more stability than the neighboring nuclei. So here they specifically given helium as an example, right? That helium is coming in one of the peaks. That means, what does it mean? If helium is in one of the peaks, that means it has more binding energy than the neighboring ones, right? Now look at the options given, right? Can easily be broken up, is very stable, can be used as a fissionable material, is radioactive, which is the most appropriate option. See, if helium is coming in one of the peaks, that means helium has more binding energy than the neighboring ones, correct? More binding energy means more stable. Stability of the nucleus is more than the neighboring ones. So which option is correct? It's B, is very stable. Okay, comparing to the neighboring elements, neighboring nuclei, helium is more stable. That is why it is coming on the peak. Okay, right. Next one, nuclear forces exist between. We mentioned this before in one of the questions when we explained. Nuclear force exists between neutron and neutron. Yes, nuclear force is the force operating between the nucleons in a nucleus, we know. See, that is the force binds all the nucleons together. So inside the nucleus we have protons. So there will be proton-proton interaction, there will be proton-neutron interaction, and there will be even neutron-neutron interaction, all paired possible. Like, the forces, they are actually, that nuclear force is charge independent, and we know this all pairs possible. And look at this, proton-neutron, proton-proton, and proton-neutron. See, the correct option is then all of this. Nuclear force is operating between all these pairs, irrespective of their charge, right? Irrespective of their properties, like they will be acting equally, that nuclear force. Okay. Now, an assertion reason question. The question, assertion statement says, the nucleus X37, right, is more stable than the nucleus. Next one is given Y3 and 4. Okay, so these are the two nuclei are given for comparison, right? And we know we have to consider that neutron-proton pair ratio, right? Then if it is more, that will be more stable. So here, go for X. In X, what is the number of protons available? We know the number of protons available is 3, right? Because that is the atomic number. Z is equal to 3, and this is A, the mass number. And what is the number of neutrons in that particular nucleus? Number of neutrons is equal to 4, correct? Because 7 minus 3, that value is going to be total number of nucleons. From total number of nucleons, we subtract number of protons. That is how we find the number of neutrons, right? A minus Z. Right, and that is going to be 4. Then, what is the number of neutrons by number of protons ratio? Number of neutrons by number of protons ratio is going to be 4 by 3 for the first one, correct? 4 by 3. Now check the second one, second element given, that is Y. What is the number of protons? In Y, number of protons is atomic number, so it's going to be 3. Z is equal to 3. Right, then mass number is given as 4, from which we can calculate number of neutrons, right? Number of neutrons is going to be 4 minus 3. 4 minus 3 is going to be 1. So what will be the number of neutron to number of proton ratio of this? It's going to be 1 by 3. Correct? So this is going to be 1.33 and this is going to be 0.33. Which one has more neutron to proton ratio? It is for X, right? Yes. So X has more proton neutron proton ratio, and we can say that this most stable assertion is a true statement. Right, now look at this. Reason R 37 contains more number of protons. X37 contains more number of protons. And that, look at that. See, X has how many number of protons? 3. Right? And number of protons in Y also is 3. See, look at that. Z is equal to 3 here. Z is equal to 3 here also. So we can't say more number of protons. No, they have actually equal number of protons. So assertion is true, but reason is false. Usually that comes under C, right? Okay, fine. So these are some MCQ questions from the chapter Nuclei, and we will discuss 2 marks and 3 mark questions of the same chapter in another video. Stay tuned. Thank you.